Hello and welcome back. These would be the notes for Chapter 7, Section 1, Solving Systems by Graphing. There is a PDF available if you'd like to print it out and follow along. First thing we want to look at is what is a system of equations or linear equations. It's simply a linear system which consists of two or more linear equations in the same variables. What we talk about by same variables is we have an x and y there, and we have the same x and y there, which are supposed to represent the same exact values in both equations. The solution of the system is an ordered pair. This is an important word here, an ordered pair, an x and a y, that satisfies both equations. So up here, the solution would be whatever x and y makes both equations true at the same time. The third thing we're going to look at here is a consistent independent system. That's simply any linear system of equations that has exactly one solution. First example, we have the same two equations that we had on the previous page, but we've gone ahead and graphed them. I'm guessing that they did this in slope-intercept form, and what happens is we have an intersection right here between the two lines, and the coordinates of that intersection is the solution of the system. So if we count it out here, we actually have a 3 for x and a 2 for y. So the solution of the system appears to be 3, 2. Now we are supposed to check it. So if we input a 3 here and a 2 in place of y, then we check to see that that equals 7. And we do the same thing down here. We put a 3 in place of x and a 2 in place of y, and we check to see that that equals 5. Okay, so on the top we have 4 times 2, or 2 times 2, which is 4, so 3 plus 4 equals 7. That one checks out. And then down here we have 9 minus 4, which equals 5. I'm just bringing this number down here, and that checks out. And because this problem or this point is making both equations true at the same time, that is the solution to the system. There is an x and a y to our system. Every system has two answers, an x and a y value, and you have to pay attention to know which one they're asked for. Sometimes they ask for both the x and the y, sometimes they ask for just the x or the y. Example 2, check your solution. Now we have to graph these, so what I'm going to do is I'm going to find the x-intercept of this first one, the x-intercept and the slope, and the x-intercept is going to be negative 3, and the slope is going to be positive 1 over 2. That's the opposite of a over b. So I can graph this by going to negative 3 on the x, 1, 2, 3, negative 3, and from there I can go up 1 over 2, up 1 over 2, up 1 over 2 a couple times. And then I'll just take my line and see if I can get it to line up here. And that looks pretty good right there, but what I need to do is extend my line all the way across, because I don't know where the intersection of these two lines is actually going to take place. Go to the next one. I'm going to go ahead and look at the y-intercept. So the y-intercept is 4. And the slope of this one is going to be negative 2 over 1. It's the opposite of this over b, so the opposite of a over b. And I have a positive 4, 1, 2, 3, 4, right there. And I have a negative 2 slope, so down 2 over 1, down 2 over 1. And we can already see where our system is going to intersect. So I don't need to make this line very long, because I can clearly see that the intersection occurs right there. The only question is, what is the value at that point? Well, we have a 1 for x and a 2 for y. So the solution of this problem is 1, 2. Now we should go back and check it, just to double check, make sure it works. So I have a negative 1 plus 2 times 2 is 4, and does that equal 3? Yes, it does. It works in the first one. And over here we have 2 times 1 plus 2. Does that equal 4? Yes, it does. So it works in both. Therefore, this is our solution. Example 3. We're going to graph this one also. This one has an x and y intercept. So the x-intercept is going to equal 5, and the y-intercept is going to equal negative 5. So 5 for 1, 2, 3, 4, 5 would be here, And then 1, 2, 3, 4, -5 would be here. So I'm just going to go ahead and use my straight edge to draw my line. Now remember, your first line always has to be the longest because you don't know exactly where these two lines are going to intersect. And let's see, on the next one I have a y-intercept of 3. So 1, 2, 3. And I have an x-intercept of 3/3, which is 1, which is right there. And now I want to go ahead and draw my line. Draw your line best that you can. And it looks like the solution is right here. And those coordinates would be 2 and 1, 2, 3, -3. And the only way to know for sure is to go back and substitute your numbers in to make sure that it actually works. So up here we have a 2 minus a -3. Does that equal 5? Yes, it does. And here we have 3 times 2 plus a -3. Does that equal 3? Well, that's 6 plus a -3. Yes, it does equal 3. It checks out there. Therefore, this is my solution. Example 4. This is a company that's renting inline skates and bicycles. During one day of business, they had a total of 20 rentals, and they collected $420. Find the number of bikes rented. Now, you have to be careful here because they're asking for a specific value, not what is the number of skates and the number of bicycles rented, but just the bikes. So we're going to write an equation. First of all, we need to identify x and y. Well, inline skates, we'll call that x, and bikes, we'll call that y. So let x and y stand for the number of skates and the number of bicycles rented in that particular day. Well, if that is true, then we know that we had 20 rentals in one day. We can simply say that x plus y has to equal 20. We also know that they collected $420. We know that we had X number of inline skate rentals, and they're selling the renting the skates at $15 per day. So that would be 15x plus $30 times the number of bike rentals, and that should equal a total of $420. Now I'm going to do the top one here in blue. I'm going to do the bottom one here in red. So the top one is pretty easy to figure out, the graph, because it has an x and y intercept of 20. So go ahead and grab this one, bring this down to 20, bring this up to 20. One thing we haven't done yet is identified x's skates, and the y value are bikes. We'll put bikes right here. When I go to graph the next one, I'm going to try the x and y intercepts and see what happens. So when I try the first one, the x-intercept comes out to equaling 28, which is 420 divided by 15. And the y-intercept ends up equaling 14. Now I can graph the y-intercept to 14, which is here, but I can't graph the x-intercept to 28 because my graph only goes up to 20. But I can come up with the slope of this line. It's going to be the opposite of A over B, which is 30. So my slope is really -1/2, down 1 over 2, down 1 over 2. So from there I'm going to go down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2. I'm going to do that a couple of times until I can get a pretty straight line. And draw my line to go through here. That looks not too bad. I think this is off a little bit. That's better. Now it appears that they intersect right about here, which would be 12 on the skates and 8 on the bikes. Now we do want to make sure that that actually works. 12 plus 8 does give us 20, so we know it works in the first one. So we're going to take 12 skates and times by 15. So 12 times 15 gives us 180, plus 30 times 8 bike rentals gives us 240. And we want to check to make sure that that adds up to 420, and it does. Therefore, the number of bikes rented, which is what they're asking for, is 8 because our coordinate is 12, 8, and y is our bikes. Therefore, we rented 8 bikes. This page here is just going to show you the 3 different types of systems. You can have a consistent independent system, as you see here on the first graph. And that means you have only one solution because the lines only intersect each other once. For our second example, we have a consistent dependent system. What we actually have are 2 lines that lie on top of each other, which makes an infinite number of solutions. So the first one, we have only one solution, which occurs here. And in the second one here, we have infinite solutions because we actually have 2 lines that are on top of each other. So every x and y in the first equation works in the second one. The third one, we have no solution because you can see the 2 lines are actually parallel to each other. They refer to that as an inconsistent system, and sometimes we call that a parallel system. So the first one has one solution, the second one has infinite solutions, and the third one has no solutions. So you should be able to recognize them by their graphs alone.